All right. The main questions I graded were 1.2, 1.24, 1.26, and 1.38. 1.24, part C, was asking you to analyze some sets and prove or demonstrate some properties. In particular, if the universe is equal to the union of two sets, and if the intersection of those sets is empty, then A is the complement of B and vice versa. And so you were demonstrating that by picking sets A, B, and picking a universe such that these things were true, and showing that A was the complement of B. And we could prove that also, but this was just playing with some sets and some operations to see that that's true. And there didn't seem to be problems with that. 1.26 was looking at infinite sets. And the first question was, if A is an infinite set, is the complement of A infinite? And it could be, but it doesn't have to be, right? Certainly if we look at the set of integers, we could set A to be the set of all integers, and the complement would be the empty set. So the complement can be finite, but you could also set A to be, the set of x and z such that x is bigger than or equal to 0. And that's an infinite set. There's an infinite number of non-negative integers. The complement of that is a set of negatives. That's also infinite. So just because we have a very large set and we're throwing all of that away doesn't mean we end up with a finite set. Could be finite, could be infinite. Part B says if A and B are infinite, is the union infinite? And that we can say absolutely. So an infinite set means it has an infinite number of elements. What does that mean? It means the number of elements is bigger than any number. Well, everything that's in the union is also in A. So the number of elements in the union is at least as big as the number of elements in A. If the number of elements in A is bigger than any number, then the number of elements in this union must also be bigger than any number. So that's enough to say this is infinite. And it kind of makes sense. Take a really big set and another really big set. You're just going to get something that's possibly bigger. It can never be smaller. And then the cross product question. And let me use different sets instead of their funny shapes, but you can do this with funny shapes, like the book. So the first thing I want to make sure is that when we take a cross product or a Cartesian product, what we're getting is a collection of tuples. And a tuple is things in parentheses separated by commas. Okay, so my first tuple will be like 1 comma A. My second tuple might be 1 comma B, followed by 1 comma C, 2 comma A, 2 comma B, 2 comma C, and so on. And that's all the 9 ways that I can take one element from this first set and one element from the second set and pair them together. And so if I'm writing this, I never would want to say that this is equal to 1A, 1B, 1C, and so on. That's not a tuple, right? A tuple's got to be in parentheses with commas separating the things inside so that we know exactly what's the first element, the second element, and if there's other elements, those as well. So if I do B cross A, that's actually the tuples where the first element comes from B and the second element from A. Right? And because these are ordered tuples, right? The ordered tuple 3 comma c is not the same thing as the tuple c comma 3. For two of these ordered tuples to be the same, the first elements have to be the same, the second elements have to be the same, and so on. So in general, the product of A, B is not the same as the product of B, A. In this case, the intersection of these two Cartesian products is the empty set. There's no tuple in here that's found in there, and vice versa. But if we have some overlaps between A and B, for example, A equals 1, 2, 3, and B equals 2, 3, 4, you can get kind of zenned out doing this. Bless you. So first element comes from B. And please shout if I make a mistake. So I think that's the two Cartesians. And so what do we have in common between them? Well, not 1, 2, not 1, 3, not 1, 4, but 2, 2 appears in both, and 2, 3 appears in both. 2, 4 doesn't show up down here. 3, 2, and 3, 3, and not 3, 4. So in this case, there is some overlap between the two Cartesian products. So what's the rule for what the overlap looks like? Yeah.
The element has to be in both sets.
Okay, so we have to deal with the intersection of both sets.
The Cartesian product of it.
If we take the Cartesian product of the intersection with itself, that looks like it's going to give us that. And we could go about proving that if we wanted to. How do you prove two sets are equal? Prove that the left set is a subset of the right, and then prove that the right set is a subset of the left. To do this, show that if something is in here, it's also in there, and then show the opposite. That's our definition of equality. Something's in here if and only if it's in there. And so you pick an element of here that looks like, you know, little a, little b, and it means that it's got to be in this set, which means a is in little a and b is in, a is in big A and b is in big B. But it's also got to be in this set, which means little a has to come from set B and little b has to come from set A, which tells you that little a is in both A and B, so it's in the intersection. Little b is in both B and A, so it's in the intersection, so this element is going to be contained in this Cartesian product. So that proves that the left side is a subset of the right. And you do something pretty similar to show the other inclusion. All right, and that was my only general comment, was make sure when you're dealing with ordered pairs or ordered tuples, put them in parentheses, comma inside. And remember that, you know, 1, 2 is not the same as 2, 1. Those are different elements. Because the order matters, that's why they're called ordered. right, so let's talk about the programming assignment, because we seem to keep forgetting to talk about that. So this may have been posted on Canvas previously and then deposted, or it may not have been posted at all. But anyway, programming assignment 1. So this is due on the 19th of February, I believe. Let me go back and look. All right, February 19th. So you got some time. All right, so programming assignment 1, you're writing a program to play around with sets. Okay, basically it's going to let you enter in the elements of 2 sets, and then it's going to do some operations on them. It'll print out the elements, tell you how many elements are in each set, and then do like a union intersection, stuff like that. Okay. Your elements that you can type in are basically any normal characters. Okay, so no weird non-printable characters, okay, no white space, so spaces, tabs, those are completely ignored. But everything else, including punctuation, is considered an element of the set. Okay, so let's run some sample code. So enter set A, PA1, hello, enter set B, cool. Okay, so you want to make sure that you're building proper sets. A set only contains an element once. If the person types in something more than once, don't make a set containing 2 L's. Okay, you got to deal with user error like that. So my set A is a set containing HELO. My set B is a set containing COL. And then tell me how many elements. The cardinality of A is 4, B is 3. The union is HELOC, the intersection is LO, and then A with B subtracted from it. So everything that's in A that's not in B, well, the H remains, the E remains, the L and the O belong to B, so those get thrown away. So the difference, A minus B, is just HE. That's what your code does. All right, so ABC, ABD, 2 sets, order of 3. Union is ABCD, intersection is A and B, and A with B removed just leaves you with C. Right, in uppercase and lowercase, everything is a separate character. Okay, don't do any case conversion, stuff like that. Don't throw anything out. So big A and little b are different. The intersection is the empty set, so I just print, 2 angle brackets. Right, ignore white space. So spaces, tabs, things like that. Just play with characters. And empty sets are legit. So A might be the set hey, and B might be the empty set. Right, if I just hit an enter, B should look like an empty set. Its cardinality is 0. So the union is just hey, the intersection is empty, and A take away B is just hey. And if I make A an empty set, and I make B high exclamation mark, right, B contains 3 characters. The union is the same as B, the intersection's empty, but now A take away B is the empty set because you're starting with the empty set. Anything more you subtract from it, you just end up with the empty set. And your final test is make both sets empty. That should work. A and B are both the empty set. They have cardinality 0, union, intersection, and difference are all the empty set. So that's, once you've got the core behavior working, start playing with empty sets, make sure that code's all solid. I won't test it with weird things like that, but but it should work anyway. But I won't use commas in your set. But technically your code should work with any characters other than white space. All right, so you got what the program should be doing. Let's talk about how we make it do that. So you're going to write a program. It should be written in C. Okay. Anybody here ever programmed in C before? Cool. All right. The universe is all non-white space characters that can be entered from the keyboard. So the program should ask the user to enter the set A, type in the elements, hit enter. Ask for the set B, type in the elements, hit enter. And then the program just goes ahead and prints out these things. So when you print your sets, ideally you're printing them inside curly brackets with commas in between. Okay? It's slightly easier to do with spaces in between, but do it with commas. Okay? And when you print the elements of B and the unions, same thing. Curly brackets, elements with commas in between. But you know, when you're developing this, don't worry about that. Just print them out side by side, or print them out one per line, or whatever you want. All right? So this is a really good example of a programming assignment that you can work up to the full solution. Okay? You've got a fair amount of time to do this, and it doesn't require you to do mallocs and pointers and lists and all this kind of stuff, right? It's more of a 224-ish style project. So you've got enough time to start off with a version that's not the version you're going to turn in, okay, but a version that you feel you can get some results from. Me, I like getting results. I like working for a little while and then having something that actually runs. And then I feel good about it, you know, and then I can make it do something more, and I feel good about that, and then I'll take the day off, you know. And then I can come back to it and add some more. And then I can add that thing that I really wasn't sure how I was going to do, and if it takes me 2 days to get that to work, you know I've gotten it working this far already, and it's enough confidence to keep going. Okay, so some details. Make sure sets only contain an element once. So if they type in the same element they've already typed, just use the first one and ignore the second one. There's a function called isSpace. You can get that from C-type. IsSpace, parentheses, give it a character. It'll give you back a true or a false. Okay? So if isSpace, parentheses, character, then you know it's a white space. You can ignore it, however you're going to do that. Or if exclamation mark is space, that'll tell you it's not a white space character. And when you hit enter, if you're using fgets, that enter puts a new line on the end. Well, new line will look like a space. If you call it space on the new line, it'll say it's a space. So if you're ignoring those, you'll be ignoring the new line anyway, which is fine. All right, empty set is valid, and if you make this in one C program, you can submit it as a .c. If you make it more than one file, submit it as a tarball. I don't know if it'll take a .tar, but make a .tar and then gzip it. That gives you a TGZ. I'll set it up to take a tar file too. Okay, simplifying assumptions. You can assume that the person is not going to type more than 120 characters. When it says enter set A, they won't go crazy and type a book. Which means that when you're using fgets, the string array that you're using to load into, you can just make that like 130 characters or something. And they won't type weird things like escape or control 2 or something. Okay, so recommendations. First thing you want to do is figure out how am I going to store a set in my program. The person's going to type in a string. I'm going to turn it into a set of characters. How am I going to store that? Probably the easiest way is an array. Arrays are kind of our go-to structure for storing a collection of things. We don't know how many things we want to store. But since all these things are characters, an array of characters is also just a string. So you could store a set as a string, just like hello, right? So if the person types HELLO and we clean out that extra L, we really just want an array containing HEL and O. And we would need a variable to say how many things are in here, so we'd have a variable equal to 4. But we already have a whole mechanism in C for dealing with arrays of characters and dealing with their length, and that is to turn them into a string, which just means put a null terminator on the end. So one way to store sets is just use a string. Make a string that corresponds to your set. But you can do it with an array as long as you keep track of how many things are in the array. And you could probably do it with some other things. You could make a linked list of characters if you want. That would be fun. But it's up to you. But a simple string will work. All right, if you want to use structures, you can. Depending on how you implement a string, structures may make your life easier, but you're not required to use them. But if I was storing an array without a null terminator, I'd need to have the array, and I'd need an integer telling me how many things are in my set. I could make a structure called set that would have those two things, an array of characters and a length. Okay, so I recommend making a function which tests to see if an element belongs to a set. I'm going to suggest that's the first function that you write. So I'm calling that a membership test function. So something like int is member, pass it a set and a character, where again your set might just be a car star, it might just be a string. And have it return some, typically an integer, 1 if it's a member, 0 if it's not. If you make this your first function, your other functions are really easy to write. If you make this and it works, right, make yourself some sets and just call isMember with different sets and different characters, make sure it's always giving back the right value. You can use this membership test function to write all your other functions. Okay, this will make your life easier if you don't want to make your life easier yet. You can do other approaches to this. So what do we have to do after this? We have to take a string that the user has typed in, we have to turn it into a set, right? So turn input into set. Maybe here's the input, and here's the, you can't, I know, and the output set. All right, so turn input into set is my function. It's going to take an input set, whatever that is, or an input string from the user, and it's going to create an output set. Okay, so turn input string from fgets into a set, which we'll call output set. So this is the preprocessor. We call fgets temp, let the user type something in. We want to make a set out of temp. Temp is a string. From fgets, we want to build a set. Make yourself a function called turn input string from fgets into a set, or whatever you want to call it. So how does this work? Make output set equal to an empty set. If it's a string, just set it equal to quote, quote. If it's an array, just set the length variable equal to 0. If it's a linked list, just set the sentinel null to point to null. So make your output set empty, okay, and then just loop for I equals 0 to length of the input if character input bracket I is not a space, then we want to add it to our set unless it's already in our set. So if the character is not a space, we can say if not is a member, output set, comma, input bracket I. So I'm going through each character. If the character is not a space, and if it's not a member of my output set already, what do? Add to output set. So that's my whole function for turning an input string into an actual set. Take each character. If it's a space, ignore it. If it's already a member of your output set, ignore it. Otherwise, add it to your output set. If your set's a list, insert it in the beginning. If your set is a string, concatenate it to the end. And there's a few ways to do that. All right, now we've got two sets that the user has typed in. We want to take the union. It's all the same stuff over and over now. So how do we take the union of A, B, and output? Copy your set A to your output. That's going to be a loop. And then for each element in B, add that to your output. So start off with your output just being equal to one of your sets, and then go through the other set element by element and add each element to the output. If that element is not a member of A. So use your membership function again. Start off with the output with A. We know everything in A is going to be in the output. Now go through the elements of B, and for each element, if it's not also in A, add it to the output. If it's in A, we don't have to add it because it already got added up here. And so this will add the new elements from B to the output, and you end up with a good set. Your goal is always to have your sets be genuine, clean sets, no duplicates. The order of the elements doesn't matter. If you want to sort it, that might work for whatever algorithms you're going to use, but in general you don't have to sort it. How do we do intersection? Start off with an output set that's the empty set. For each element in A, if that element is a member of B, add to the output set. To go through each element in A, if it's a member of set B, add it to the output. That will build the intersection for you by definition. A take away B, set your output to the empty set. Go through each element in A. If it's not a member of B, add it to the output set. So if you can iterate over the elements in your set, which if it's a string is just, for I equals 0 to string length -1. If you can iterate over each element of the set, tell if something is a member of a set, and add an element to a set, right? This is all pretty straightforward. Right? Assuming you start with those three capabilities. Okay? Now if you just start trying to write a union function, trying to write an intersection function, each one's going to take a chunk of work. Right? And you're going to be kind of repeating that work again and again. And a mistake in one might trip things up. So that's my suggestion, right? Start with a membership function and think about how to loop over the elements of a set and how to add elements to a set. and then think about pseudocode like this. Does that make sense? All right, so make sure you turn in C code that will compile, and I will download it from Canvas. I'll put it on my test account. I'll compile up your program, and I'll run it on various test cases, and see how well it works. All right, define the membership test function. With that, you can build input, union, intersection, complement. I guess that's my only recommendation. Other than start early. All right, any questions? Yeah.
So we have pretty good leeway though in terms of how to implement it.
Yeah.
You were mentioning we could do things like
Yeah, if you want to make a linked list implementation, that would be fun, I think. Membership is just a search function. Adding is just inserting the beginning, and telling how many things you have in the list is just your list length function. So I mean, the stuff you're doing for PA3 works really nicely for this, PA3 and 222. Yeah?
Are you requiring any functions like specifically?
No, all I want is your main program to work.
Cool.
So if you want to just do it all in one big main program, that'll get you points if it works. Get you full points. All right, so I'm going to compile with just plain old GCC. If you have multiple files, give me a make file. If you give me multiple files and you don't give me a make file, I'll just GCC everything together. And if that's not the right thing to do, then I can't build your executable. So if it's not just compile everything, give me a make file. Yeah?
What if you don't remember how to do C programming that well?
Talk to me. Okay. There are some people in here who are not in 222, or more particularly who are not in 224. And if that's your situation, come and talk to me. Shoot me an email, right, and let me know. And in the past, what I've done in that situation is just sort of, you know, more leeway, but mostly, you know, asking you to start early, let me know where you are, and we'll work through it like that.
You can write it in binary if they don't
Yeah,
see.
right. Do machine code. I had a teacher when I was an undergrad for a course, and he said, you can use any language you want. And my friend and I took it as a challenge to find the most bizarre esoteric languages and use a different one every week for the homework, just because we were jerks like that. I used APL, I used Spitball, I did at least 2 assembly languages, one on Z80 and one on Vax Macro, and somewhere around that point he sort of like asked us to take pity on him, and so I stuck with C after that.
We do Fortran.
Oh yeah, totally Fortran.
Okay.
Yeah. Fortran was like one of my first 3 languages.
What was your first language? English?
Technically my first language was an HP 9820. It was a programmable calculator. But my first programming language was BASIC, right? Vax RISC-E system. And then it was APL, and then it was Fortran. Yeah. Is that helpful? I cannot swear to you that it conforms exactly to the. Let me make myself a note, and I will make sure that conforms, and I will post an example.
Was it Spitball or Snowball?
I learned both. Spitball is the faster version of Snowball.
Whoa.
Yeah. All right. I will post a sample probably tomorrow. Snowball, Spitball, they're string processing languages, but you can do a lot of general computing just in a string processing language. Alrighty. And have I posted homework for next week? That's interesting. Well, Wednesday is the midterm. Yeah, I'll post some homework today or tomorrow. But I'll probably make it due like next Friday or the following Monday. We're talking induction, and it's kind of a larger unit to get through anyway, so. But I'll post up some homework tomorrow. All right, so questions so far on induction or anything? All right, so let's run through another postage stamp example, and then let's talk about where that leaves us. So, theorem. Given an infinite supply of 3-cent and 7-cent stamps, 3s and 7s, you can make any exact postage greater than or equal to, I think 17 cents will work. So just 3s and 7s, you can make any postage 17 cents or more exactly. So 17 cents would be 2 7s and a 3. 18 would be 6 3s. 19 would be 4 3s and a 7. 20 would be 2 7s, 2 3s, and so on. And we claim that you can always do this for anything 17 or greater. So let P of n be the proposition you can make n cents postage from 3-cent and 7-cent stamps. Again, P of n doesn't say anything about 17. P of n is just a proposition about n. P of 5 says I can make 5 cents postage from 3-cent and 7-cent stamps. P of 5 is false. Right? I can't get 5 cents out of just 3s and 7s. But P of 5 is still a proposition. Okay? This theorem claims P of n is true for all n bigger than or equal to 17. That's what we want to prove. Okay, so let's have a base case. P of 17 is true because 17 equals, whatever it equals, 1 times 3 plus 2 times 7. So what's left to prove is that if P of n is true, P of n plus 1 is true. And that this is true for any n we pick bigger than or equal to 17. So step 1, P of n, that's our hypothesis. Step 2, n equals something times 3 plus something times 7, right? That's the definition of p of n. So let me call it x times 3 plus y times 7. So because p of n is true, we can write n in this way. Okay, and now we're going to have a couple of cases. Case 1 is the following. Let me think about this, because it's been a while. If we have at least 2 3-cent stamps, in other words, x is bigger than or equal to 2, then we can take away those 2 stamps, add a 7-cent stamp, and that's going to leave us with n plus 1 cents. Okay, what's going on here? 3x plus 7y. Well, I'm taking away 2 times 3 is 6. I'm adding 1 times 7 is 7. Take away 6, add 7. Our postage has gone up by 1. You can expand this and convince yourself if this is true, then that is true. But the intuition is, if we have at least 2 3-cent stamps, peel those off your package, replace them with a 7-cent stamp. We've got 1 cent more postage now. If that is not the case, if we don't have at least 2 3-cent stamps, we'll do the following. Well, x is less than or equal to 1. Either we have 1 3-cent stamp or we have no 3-cent stamps. N is bigger than or equal to 17, so y has to be at least 2. If we only had 1 7-cent stamp and we only had 1 3-cent stamp, our total postage would be 10, right? But we've been told that our total postage, n, is at least 17. Now we could have a 3-cent stamp and 2 7-cent stamps. We could have 3 7-cents, we could have 4 7-cents, and so on. But we have at least 2 7-cent stamps. We have at least 2 7 cents. Well, we can take any 2 7 cents, pull them off the package, replace them with 5 3-cent stamps. So we've pulled off 14 cents in postage. We've added 15. Our total postage has gone up by 1. And if I write that in the mathy way, x plus 5 times 3 plus y minus 1 times 7 is going to be n plus 1. Sorry, y minus 2. Right here we're pulling off our 14 cents. Here we're adding 15 cents. Total postage goes up by 1. So if x is at least 2, this is a valid combination because this will not be a negative number of 3-cent stamps, right? And we'll get n plus 1. If x is not at least 2, then we know that y is at least 2, and so this is not a negative number, so this is a valid combination of 3s and 7s that gives us n plus 1. And those are the only 2 possibilities. Either we have at least 2 of these or we don't. And so in either case, we can get n plus 1, and therefore p of n plus 1 is true. And so p of n implies p of n plus 1, and therefore p of n itself is true for all n bigger than or equal to 17. End of a proof, we can say QED. Don't write QED though, just for like the answer to an arbitrary question, like if a question says what's the union of these 2 sets. When you write down what the union is, that's not a QED. Okay, right? QED is Latin for which is what we were asked to demonstrate. So it goes at the end of a proof once you've demonstrated what you were asked to show. We wanted to prove P of n for all n bigger than or equal to 17. We proved P of n for all n bigger than 17. We're just reminding the reader this was what we were originally trying to show. So that's another classic inductive proof, right? And in this case, we did it with two cases. But again, this gives us an algorithm for making postage. If we want to make 18 cents postage, and we can't think of, oh, let's just use 6 threes, we can use this to prove that we can make 18 cents postage, but the proof of that will actually give us 18 cents postage. How do we do that? Well, we start off with 17 cents postage. We have a solution for that. We know that to make 17 cents, we're going to do the following. 17 cents. Our base case is telling us we need 1 3-cent and we need 2 7-cents. Okay. If we want to make 18 cents, well, this prescription tells us how to go from 17 to 18. If we have at least 2 3-cent stamps, well, we don't. We only have one, so we're in case 2. In case 2, we're going to replace 2 of the 7 cents with 5 3-cents. So we're going to come down to only 1 of these, and we're going to go up to 6 of these. That's not right.
Sorry, 6 and 0.
Yeah.
Subtract 2.
Oh yeah, subtract 2. Thank you. Okay, and there's our 18 cents. What if we want to make 19 cents postage? This tells us if we can make 18, we can make 19. How do we do it? See which case you're in. If you have at least 2 3-cent stamps, well, we do. Right, we have at least 3 of these, so it says take away 2 of those. So let's go down to 4 and add 1 7-cent. So 4 and 1, that's 12 and 7, there's 19 cents. If we want to make 20 cents, we know how to make 19. Which case are we in? Do we have at least 2 3-cent stamps? Yes. So decrease this by 2, increase your number of 7s by 1. There's 14 and 6, there's 20 cents. So even though we were trying to prove this proposition, we, in the process, came up with an algorithm for actually making postage. Well, we can keep doing this, right? We can go from here to 21, 22, 23. We could write this as a function. And if you want to make 95 cents postage out of 3s and 7s, we just keep doing this until we get up to 95. Right? So we do this 79 times, and there we go. Yeah.
So, where did case 1 come from?
Case 1 came out of my head. Right? So this is that bridge that we cross that tells us how to get from n to n plus 1. And but having done these problems before myself, right, my goal is how can I increase 1 cent, right? And so thinking about 3s and 7s, well, 7 is 1 more than a multiple of 3, so I can take away that multiple of 3, 6, right? But then what if I can't take away 6 cents in 3s? What if I don't have 2 3s? So I got to find some other combination of 3 and 7 that'll go up by 1. And so just playing around with it, it's like, oh yeah, take away 14 and add 15. But it's kind of trial and error. This works well with numbers that are relatively prime, because we're kind of doing Euclid's algorithm here, but don't worry about that. There's some things that this does not work with. For example, if you had 3-cent and 6-cent stamps, there's postages you cannot make. Right? You're never going to get 7 cents postage. You're never going to get 61 cents postage out of just 3-cent and 6-cent stamps, because adding 2 3s is the same as adding a 6. So you may as well just have a batch of 3s, and with 3s you can only make postage as a multiple of 3. Right, so we, in US currency, we have 1, 5, 10, and 25 for our metal change. And that's sufficient to make any amount of pennies from 1 through 99. Right, well, if we've got a 1, we're always set. What if we didn't have a 1? What if we only had 2s, 2 penny, 5 cent, 10 cent, and 25 cent? What postages could we make or not make? We couldn't make 1 cent, but could we make everything else? Right, so this is, you know, the kind of theorem proving you do if you had taken over the government and were starting your own currency system. And it's like, well, what denomination should we use? So there's your niche in the new order. So what is it like to code this, right? We could make a big for loop, and, you know, for postage equals 17 up to whatever postage we're after, and just keep making these adjustments, right? See if it's bigger than that, and do this, and so on and so forth. And that's not too bad. Yeah?
Essentially, you could just maybe something like a matrix stamp, if you've got the x plus y equals n.
Mm-hmm.
Is that any sort of what you're going for? And then do that?
Oh, interesting. Do a simultaneous equation kind of thing. That would be cool. Simultaneous equations, or equations like this in general, in integers are very interesting. It's something called the Diophantine equation. The Greeks studied these a lot. In KVL, KCL, you're solving equations. Your solutions could be whole numbers, or they could be, you know, 2.56 amps or things like that. If you restrict yourself to integers, it's a really interesting area. We're going to talk number theory after this unit is done, and we'll see some of the things related to that. So let's think about a different way to code this, because we have an algorithm here, right? And to solve 21 cents, I don't need to start with 17 cents. If I know how to make 20 cents postage, it takes me 1 step to get 21 cents. Right? If I want to make 95 cents postage and I already know how to do 94 cents, it takes me 1 step to figure out the solution for 95. So we're going to do this thing again where we call on our friends, and, you know, someone hires me to make 95 cents postage for them out of 3 and 7 cent stamps. And I say, yeah, I'll have a solution for you tomorrow. And as soon as they leave, I text my friend who does 94 cents, right? And I say, hey, can you make 94 cents postage for me? And they give me a solution, and I just tweak it using one of these 2 cases. And I didn't have to do, you know, 95 operations. I just got somebody else to do the case for 94, and I made 1 adjustment to it. And my friend had another friend, and texted them and said, can you do 93 cents? And she's like, sure, and she sends back a solution for 93 cents. And then my friend just has to make 1 change to that. Gets the answer for 94, gives that to me, I make 1 change. So we're distributing the load. Each of us only has to do 1 operation, either take away 2 3s and add a 7, or take away 2 7s and add 5 3s. So none of us have to work very hard. You just need a lot of friends. And then we're going to do the thing we did the other day with floor tiling, which is, you know, admit that we don't have any friends. And so we sit at the table and we write down, you know, what's the postage for 94 cents, and we go out the front door and we change our clothes and come in the back door and say, oh, question, 94 cents, okay, let me work on that. And we go into the other room and we say, you know, solve this problem for 93 cents, please. And we go out the door and come back in, and we solve that problem by going to another room and saying, solve this for 92, right? And eventually, we come in the back door, and there's a piece of paper that says, can you solve this for 17 cents? And we say, oh yeah, that's a base case, just 1 3 and 2 7s. We write that down, we're done. Now we go back in, and the person who was trying to solve 18, suddenly the solution for 17 is there. They do one of these cases, they've got a solution for 18, they write that down. And now they're done. And we keep going, and eventually I'll be back in my original clothes, and I'll come into the back door, and there's a solution for 94 cents. and I apply whichever case is relevant, and I've got my solution for 95. Okay, so you look goofy if you do that in person, but computers don't mind looking goofy. So so here's the equivalent of that in C, and remember when we pass variables to a function in C, it's hard to change the value of that variable inside the function unless we pass the address of it, and we say star variable equals. So don't get tangled up in the star and the ampersands here. I just want to look at the general way this works. So I'm going to ask for how much postage you want. I'm going to call fgets. I'm going to scan it. If it's less than 17, I'll ask you to try again. Otherwise, I will call this function solve. I'll pass it the total postage I'm after, and it will fill in the number of 3 and 7 cent stamps that I need. And then I'll just print out number of 3 cent stamps is whatever 3 is, number of 7 cent stamps is whatever 7 is, and I'll go back and loop again. So this works fine, right? 17 cents, that's 1 3 and 2 7s, right? So 1 and 2. 18 cents is 6 and 0, right? That's what we got. 19 cents is 4 and 1, that's what we found there. 20 cents should be 2 and 2. And if I want 95 cents, it's 6 3-cent stamps and 11 7-cent stamps. So 77 plus 18, that's 95. And if I want some crazy amount of postage, right, you can get a little insane. All right, so why did that dump my core? So let's look at the code for solve. So I pass in the total. I'm going to fill in 3 and 7. First thing I do is see if this is my base case. And I shouldn't call this for something less than 17, but if I call it for 17, I'll say give me 1 3, give me 2 7s. We're done. I've hardwired the base case into this. Okay, I have coded this P of 17's proof. Okay, otherwise, what do? I say, hey, magic function, give me a solution for my total minus 1. Okay, that's calling my friend and saying, hey, can you give me the solution for 94 cents? My friend is my solve. This is the function called solve. I'm saying, well, let's use this function, which I know works because I just wrote it. Let's use that to solve the problem for total minus 1. So when I come back from that highlighted line, 3 will be the number of 3-cent stamps I need, 7 will be the number of 7-cent stamps I need. And then I have 2 possibilities. If there's at least 2 3-cent stamps, I'm going to replace one of the 7 cents, replace those 2 with 1 7-cent. So if the number of 3-cent stamps is at least 2, I'll subtract 2 from that, and I'll increase the number of 7s. Otherwise, there's only 1 3-cent stamp. There must be at least 2 7-cent stamps. So I'll replace the 2 7s with 5 3s. Take away 14, add 15. So subtract 2 from the number of 7s, add 5 to the number of 3s. That's the end of the function. So other than the base case where they ask for 17, this is really all we got to do. And most of this is comments, right? Solve it for total minus 1, and then adjust the number of 3s or 7s based on which case you're in. And that actually works. Okay, so that's what we call recursion, or a recursive function. And the weird part of it is it's using itself. It's a function called solve, right? This is solve, but it's using itself to solve the problem for a simpler case.
So do you Stack Overflow because those are the, or was that a Stack Overflow?
Yes.
Okay.
Yeah. So so if you call yourself too many times, right? We talked yesterday in 222 about the stack. And the stack is used every time you call a function. Well, each time you call this, it takes more stack space. Eventually you run out of stack space, you get a seg fault. So there's a limit to how many times we can call ourselves. But you know, theoretically, if we keep calling ourselves with total minus 1, what's going to happen? Eventually we're going to call ourselves with total equal to 17. And this is going to fire. And we're not going to call ourselves again. We're just going to set an answer and return. That pops us out of our recursion, and we start coming back up this chain of calls, and eventually we'll come back to our original call from main, this call up here, and then we'll go ahead and print our answer.
So provided you initialize 3 and 7 to 0, could you have your recursive call at the end and build the stack the opposite way? That would still work.
Yes, yeah. Yeah, so that's something called tail recursion.
How do you decide between those two types of recursion? Is the former one called head recursion? Or
I don't know if the other one has a name.
Okay.
I usually hear tail recursion, because tail recursion you can always replace with just a loop.
Yeah.
Right, you can just go back up to the top and keep track, which is what we're doing here basically. But there's a lot of cases, and most of the interesting cases that doesn't work. So if it works, go with tail recursion or just make a loop.
Oh, so the other kind of recursion is usually more.
Yeah, usually you're calling yourself multiple times inside the function. And we'll definitely get to plenty of that in 222.
Right, so in this case, it depended on 3 and 7 being initialized to 0,
Mm-hmm.
which may or not be possible.
Yeah, yeah. All right, so does that seem a little weird to anybody? This idea of a function calling itself, right? This is one of these things that may, you know, alternate between seeming totally bizarre, seeming completely obvious and logical, what's the big deal, to seeming like, well, there's got to be something cheating going on here because I'm not doing any work, to something that's like, this makes no sense, I hate this, right? Generally, we'll bounce around a bunch of different ways that this is sitting in our brains, right? That's how we get more comfortable with it. Eventually, right, this will seem very natural and logical to you. And when it does, then it's a really powerful tool to pull out. And when we get, by the time we get to the end of 222, we'll be doing recursion as if it's the most natural thing in the world. We'll be using it to explain a lot of how we manipulate data structures. But at first, in particular, it's going to seem weird sometimes. That's okay. Okay, we'll spend time working into it. I'm curious what this is. I'll check it later. All right. So back to induction, right? So induction and recursion are related. We solve a problem. We prove that we can solve the problem. They're sort of similar. The other thing is, when you write a function to do something, you'd like to know if it's correct. Now you write code, you know this from ODPs, you write your function and you test it in a few cases and it works great, but you send it in for assessment and it doesn't get you full points because there's some case you forgot to check, right? Well, so we just tried the stamp code for a few numbers and it seemed to work, but how do we know that it always works? How could we prove that this function solve will always give you a solution for a number total bigger than or equal to 17? Two-word answer, mathematical induction. Right? We can use induction to prove that this function works. How? Let P of n be the proposition that solve n always gives you a correct answer. Okay, we need a base case. Can we prove that this works for total equals 17? That's pretty easy to believe, because if total equals 17, it's going to return 1, 3, and 2 sevens. That's a good solution. So our proposition that this works for some given total, it's definitely true if total equals 17. So P of 17 is true. Now we just have to prove that if this works for n, it works for n plus 1. Or if it works for total, it works for total plus 1. Or if it works for total minus 1, it works for total. All we have to prove is that if this function works for total minus 1, it works for total. So assume it works for total minus 1. Well, in that case, this is guaranteed to give us the correct solution. And we know that if 3 and 7 is the correct solution for total minus 1, it's pretty easy to convince yourself that these will give you a solution for total. So we can prove, in this case, P of n minus 1 implies P of n. That's a good inductive step. Together with the base case, that proves P of n for all n bigger than or equal to 17. Ergo, this function works. It's a good Friday thought. All right, questions? We've got 10 minutes, 5 to 10 minutes. I want to talk about odd pi fights. So if you have an odd number of people, each person has a pi, and you throw a pi at somebody else, under which situations does somebody survive and not get hit by a pi? And we can prove a theorem about that using induction. It's called the Odd Pi Theorem. But let me leave you with something different. Let's prove that all unicorns are the same color. Okay, so what color are unicorns? Or what colors do they come in? Rainbow, obviously, right? Anything else? White, pink, right?
Glitter.
Yeah, glitter. So we know that unicorns come in different colors, right? But let's prove that that's not the case. Let's prove that they're all the same color. Okay? So let P of n be the proposition in any group of n unicorns, all n unicorns are the same color. And let's prove P of n for all n bigger than or equal to 1. Okay, we need a base case. P of 1 says if you make any collection of one unicorn, every unicorn in that collection will be the same color as every unicorn in that collection. If we have a parking lot and there's one unicorn in there, is every unicorn in that parking lot the same color? Right? It's a sort of default base case. P of 1 is true. And that's not a trick. That's not where the problem is going to be. P of 1 is definitely true. Okay, so assume P of n. Let's prove P of n plus 1. And I'm going to present this and I'm going to ask you to think about it, and we'll talk about it on Monday. If you see what the issue might be, we'll talk about it on Monday. Okay? So let's assume P of n. Okay, well, I'm going to get my unicorn corral. And I'm going to have n unicorns. And they're all the same color. Because that's what P of n says, and we're assuming P of n. Okay, so we've got unicorns 1, 2, 3 up through n. Well, now let's make a bigger corral. With space for n plus 1 unicorns. Now we know P of n is true. We know if we take any n unicorns, they're all going to be the same color, right? So I'm going to just look at these n unicorns, put them in a corral. They're all going to be the same color, right? That's what P of n says. I'm also going to take, right, after I do that experiment, I'm going to take these n unicorns, 2 through n plus 1, put them in a corral. That's n unicorns. They're all going to be the same color, right? Well, if all of these unicorns are the same color as each other, and all of these unicorns are the same color as each other, they all have to be the same color. right? Because this one's the same color as that, and that, and that, and that. And this one is the same color as that, because it's part of this group of n. And so we have n plus 1 unicorns, and they're all the same color. Therefore, we have p of n plus 1. Therefore, p of n implies p of n plus 1, and so p of n for all n bigger than or equal to 1, so all unicorns are the same color.
How do you know the 2 through n plus 1 case?
How do you know what?
When you drew this
2 through n plus 1? Because that's n unicorns. Right? Take those, put this one in 1, put this one in 2, put this one in n. That's a collection of n unicorns. And any n unicorns are all the same color. That's what p of n says. Yeah. So that's a mathematical induction proof that all unicorns are the same color, or all horses are the same color, or all people have the same name, or whatever you like. So think about that and see if you can figure out what the problem is. We will talk about that on Monday. We'll talk about odd pi fights. We'll go through a few more examples of induction. We'll talk a little about the midterm. We'll have the midterm on Wednesday. We'll review the midterm on Friday and start our next unit after that, which will probably be number theory. All right, have a good weekend. I will be in office hours right now, so if you want to talk about 222 or 215, come by. I should be in there.